Hi everyone. Today we're going to learn about geologic history. One of my favorite topics of all things. It's hard to believe that one can get excited over geology, but I just find it absolutely fascinating. Just to take, for instance, the fossil that you see there. Probably we'll be looking at something from about 200 million years ago. But the bizarre thing about that slab is that it's more than likely coming from the Appalachian Mountains. And that's obviously a fish. It looks like a dolphin, but it's not a mammal. We don't have any mammals from that time period. But, like, how does a fish get to a top of a mountain and get buried and turned into a fossil? It's just mind blowing. And the key thing here is having enough time for these kind of events that could make that happen to exist. All right. So we're going to talk about how old we think the Earth is, according to the geologist, and look at the evidence that they have for that, because it's really important to understand how geologists think, and then take a look at some of the changes that we've seen in Canada over time. So I got a great video here for you. So please watch the video about the Grand Canyon. It's pretty fascinating. I realize Grand Canyon's not in Canada, but hey, it's cool anyway. So how do we figure out how old something is? So there's a basic thing called relative versus absolute dating. So for instance, relative dating would be saying, well, you are younger than your parents, but you're older than your little child sibling. So you've sort of bracketed. You know that you're somewhere between this age and this age, but we don't know exactly. And so when we take a look at a diagram here of rocks, if we were to drill down through this, we would assume that the stuff on the top is the youngest, stuff on the bottom is the oldest. I'd like you to click on the relative dating here. It brings up a little pop-up, and it's a really cool animation showing you how this works and how sometimes it gets really messed up with how faulting and folding can really change the layers of the rock. So this is a simple diagram showing how basically the bottom of Lake Ontario, we've got dirt accumulating year after year after year, and then the stuff on the bottom gets so compressed, although the air pockets and the water get squeezed out of it, and it gets made into, if it's sand, sandstone, if it's mud, maybe slate or mudstone. And then there might be a crack that develops and it fills up, and then that's yet another layer. But obviously, this layer must have been created after the other layers have been created. So, before I get into absolute dating with carbon, there's other ways that we have figured out how to date things. And I think they're pretty cool. Everybody knows about trees. We got those tree rings. And so, if we've got a specimen here that we know when it was cut down, we can just simply go back in time and we can see what the climate is like from year to year, because that's going to tell us what the thickness of the tree ring is. But on top of that, we know that this tree would be X number of years old. Now, what's really cool is what we can match up the sequence of thick, thin, thick, thin, thick, thin, whatever of tree rings. And if there's, for instance, a dead tree that's at the bottom of a bog that's near there, it might extend our knowledge of trees even further back, because we could find a tree that has this sequence here, but extends another 400 years prior to that. So we really can get some interesting understanding of history through trees and taking a look at the tree rings and understanding how far back in time we can go with those. Ice is another great way. It's a great time sequence. Basically, we have all the accumulation that occurs during the winter, and then we get a little bit of melting. So you can see the thickness there. That's the melted ice or the melted snow that turns back into ice. Then we get an accumulation of snow, ice lens, and so on. And then eventually it all gets compressed into glacial ice. So this is a sequence of, you just need to count, 1, 2, 3, 4. Those are the years, right? The further down the glacier you go, the older it is. So using glacial ice, we know that the planet is at least 250,000 to 300,000, years old, because we've drilled to the bottom of the ice cap in Greenland, and we can count that high. So we know for sure that we're looking at that sort of age for the ice or for the glaciers of Greenland. So then we can also take a look at actual trees that are still alive. Did you know that there's a tree that's 4,862 years old and still alive? Oh, sorry, no, cut down. Where's our oldest living one? Dead, 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 dead. Maybe these ones are living. But, the idea that this thing, oh, here we are, alive. This one's 3,649 years old. Wow, that's incredible. And then finally, I was showing you the clay, the sequence of dirt on the bottom of the lake. We call those varve clays quite often. So if it's near a glacier, so during the summer, a glacier melts, it takes lots of water to a close by lake and dumps a whole bunch of sand and silt and so on into the lake. Now, during the spring rush of melting, quite often you get a lot of gravel. And then as the summer progresses and there's less and less rain, you get finer material. And then throughout the winter, you get really fine material. So you get this funny layering once again of different types of material, the coarse stuff versus the fine stuff. And you can go back and you can look at near glaciers, the sequence, and count back thousands and thousands of years um, of the deposits. So that's one way we can count back in time and get an idea of the age of stuff. But we've also got this great thing called carbon 14 dating. And if I can just present this for a sec. Hey, why is it not going there? There we go. Gotta click on that. What? It's not working anymore? Oh, no, that's too bad. Essentially, with carbon 14 dating, basically there's this special form of carbon that we find in living things. And as soon as an object dies, like our crocodile or our plant, um, the the amount of that special kind of carbon atom starts to decay. And the longer something has been dead, the greater the amount of decay that has occurred. And it's a very predictable decay rate. Just like, for instance, when we have a nuclear reactor, we've got nuclear, um, we're creating nuclear energy, there's this radioactive decay of the material that we're using, the plutonium and so on. And it decays at a predictable rate. If it wasn't predictable, we'd have, if it suddenly sped up, then all of a sudden we'd have all this radioactive material shooting all over the place, and it would be an uncontrolled reaction, and that would be really bad. Well, the thing about carbon is it decays at a predictable rate. So if we just take an object and examine the carbon in it, we can get an idea for how long ago that object died. So um, so it really allows us to do a great job of dating anything that has carbon. Now, don't forget, fossils don't have carbon. So we don't use carbon 14 dating on fossils of dinosaurs or anything on that line. We use it for things that still have carbon in it. And a fossil doesn't have carbon in it. But let's say I find a piece of paper in a tomb in a brand new pyramid or a recently discovered pyramid in Egypt. What we do is we rip little pieces of that paper and send it to 3 different labs around the world and go, okay, you go figure out the age of that paper. In the meantime, what we're going to do is look at the hieroglyphics at the wall, the stories that they're telling, and compare that to what we know about Egyptian history. And our historians are going to come back and they're going to say, well, it's somewhere between, I don't know, 1500 AD or BC and 2000 BC. And the great thing is that those labs are going to come back and they're going to give you a specific date. They're going to go, well, that piece of paper started to well, it was from a tree that was cut down approximately 1,672 years to 1,675 years or something along that line. So it's pretty good, and you'll get the three what's called labs coming back with pretty close numbers. So because we can triangulate like that, we've got various different sources that are able to confirm that carbon-14 dates work. We find it pretty trustworthy. Now we can also test fossils, not with carbon-14 dating, but there's like a cesium dating. It's using an element that's in rocks, and that's how we figure out the age of rocks. All right, so what does that come up with? Well, it gives us an idea that our planet is about 4.55 billion years old, according to the scientists. And there's sort of common characteristics for these big periods of time. And the key thing is that we see a mass death on the planet after each one of these eras. So furthest back in time, we've got the Precambrian. It ends at about 542 million years ago, and there's a massive extinction event that occurs, and then we don't really know much about what caused that one. But then we've got the Permian Extinction. It's called the Great Dying. Even worse than the dinosaurs, it was like 95% of all life on the planet died during that period. They think it may have been from a massive volcanic eruption that created the Ural Mountains in Russia. Just completely messed up the climate and acidified our oceans and killed everything in the oceans. It was pretty bad. And then, of course, everybody knows about this 65 million years ago. That's the big asteroid that hits off hits part of the Yucatan and into the Gulf of Mexico, and hits at a really bad angle. Like if it had hit straight on, it probably would have been better, but like it's just a series of bad things. That part of the ocean has a lot of sulfur in it, and so when it hit, vaporized, puts all this sulfur into the air, and sulfur is really bad for for staying up in the atmosphere for a long period of time and blocking out the sun. And the dinosaurs, let's face it, they weren't doing well by that time period anyway. They were sort of in suffering a lot anyway, but this sort of tipped them over, and that was the end of most dinosaurs. Of course, we still have dinosaurs. Take a look at the chicken that you ate for supper. That's a little dinosaur that you ate. And now we're into the Cenozoic. Some people are arguing we're going through another great dying as the mass extinction of all types of species except for humans on this planet is occurring. So we're going to go through each one of the eras, look at the geology of what changes in Canada, and then what sort of fossil record we find at that time. So I'm going to go through this pretty quickly. You can copy it down into your notes. But essentially, our oldest part of Canada is the Canadian Shield. That's northern Ontario, and it's that ring that goes all the way around Hudson Bay. If you take a look at the rock there, it's super ancient rock, and essentially what you're looking at is the roots of mountains. We used to have mountains the size of the Himalayas here in Ontario, and they've just worn down because they've been around for so long. Ice and snow and running water has just worn them down to the roots of mountains, and that's why we only have um, basically rolling hills in the Canadian Shield. If we go looking for fossils, we don't find much. We find bacteria and some multicellular organisms, but it's pretty boring. There's not a lot of life that we can find evidence of for that time period. So this is the part of North America that was above water. That's the Canadian Shield. Big mountainous area. As it erodes away, it's dumping all that dirt down here in southern Ontario where we are. We're underwater at that time period. But it's slowly getting shallower and shallower and shallower, so shallow so that we can actually have coral reefs that start to develop. And that brings us to the next era, um, which is the Paleozoic. And what's going to happen is we're going to have two plates colliding. We've got the North American plate and the Eurasian and the African plate, and they bang, smash all together, and they fold up all the ocean bed between them. Um, but before that, we've got that coral reef. And when you take coral and basically cover it up with a whole bunch of dirt, a bunch of sand, and so on, and then compress it over time, boom, you know what you get? Limestone. And what do we find here in Niagara? You can go to the Brock University and take a look in the along the escarpment near there, and you're going to find fossils of coral, and that's because of the ancient coral reef that used to be here. You're also going to find sandstone, a lot of sandstone in the area because those were the sandy beaches areas that were close to the what's that called, coral reef, and eventually buries it. And there's a piece of coral, one of the ones that you can easily find here in Niagara. So the Paleozoic, we've got the collision of those three different continents, folds everything up and makes this big mountain range that extends all the way down the North American eastern coast. It also folds up the mountains in places like Norway, Scotland, and the Atlas Mountains of Africa. And because we have that tilting and folding of land, we've got all the Great Lakes region rising above sea level, so we're no longer underwater. And our fossil record shows that there's lots and lots of fish. So we have this explosion of all these different species of fish. We get the megalodon here, and and we also see early, like, big, huge killer frogs and weird looking reptiles on land. So I got a great video here of some of the weird looking fish that evolved during that time period. So take a look at it. Now I've got the Mesozoic. Everybody loves Mesozoic because it's the age of dinosaurs. It's broken up into three eras. You've heard of the one, the Jurassic, but there's also the Triassic and the Cretaceous. And funny enough, Jurassic Park, most of the species that you see in the film are not from the Jurassic. They're actually from the Cretaceous period. But that's all right. We get these big flying reptiles. They're the size of a plane. These are fossils that we found out in Mexico. That big supercontinent, you know how I said all the continents sort of smashed together? Well, it's starting to split apart. We got sort of a big northern chunk and a southern chunk, and North America has this sea that runs through the middle of it. And this is why when you go to Saskatchewan, you find a lot of potash. Now, potash, if we were to take, let's say, the Black Sea or the Mediterranean Sea and close it off and then let it dry out, you'd be left with all these minerals from the ocean. Well, that's potash. So when you find potash, you think, oh, there must have been an ancient sea here, and hence why Saskatchewan has the largest deposit of potash on the planet, because as the inland sea in North America dried up and got smaller and smaller and smaller and smaller, it was the remnants of it was in Saskatchewan, and it left this that big deposit. Surrounding that inland sea was a big swampy area, and so Alberta, which was the big swampy area in Canada, had lots and lots of material falling down into it, getting covered up, and eventually that stuff gets turned into oil. So we have one of the largest deposits of oil in Alberta because of the swamps that were commonplace in North America during this time period. All right, Age of Dinosaurs. We get some pretty funky things. Albertosaurus. We've got all sorts of like three horn, the Triceratops, but we also have Centrosaurus, which only has one big horn. We've got oh shoot, there's one with Styracosaurus, I think it is. It's got like a whole frill that horns go up instead of forward. Anyway, it's pretty interesting stuff. Go to the Royal Tyrrell Museum if you ever can in Alberta. It's pretty amazing. And then it all comes to a smashing end. Great little video here explaining the last day of the dinosaurs. And then we're into our last era. So the last era is characterized by not a lot of plate movement because it's a short period of time, only 65 million years. But what we do see is a lot of glaciation. We have four big glacial periods, and they basically scour out the Great Lakes. We've got this 2 kilometer thick chunk of ice, like a bulldozer, pushing down into southern Ontario, and all the soft rock just sort of gets scooped out by the glaciers, and then when they melt, they fill up the big holes that they left behind. Um, We also have a plethora of mammals. The largest species on land. In the oceans are the mammals, so they're the age of mammals. And we start finding or not, yeah, is it fossils? I don't think they're actually fossils. I think they're actually just bones of humans towards the end of this era. So wherever you see a hand, you should be writing down the contents. I know it's a lot, but it's really a fascinating look back at how Canada's landscape has changed and the causes for those changes, and also the causes for the change of the wildlife. Take a look at this. These are some of the big super species we used to have in North America that have all gone extinct. Extinction occurs all the time. It's just that humans are speeding it up right now. You're going to do the map of Canada and identify the major landform regions. The Western Cordillera, a big mountain range that consists of the Rockies, the Central Plateau, and the coastal mountains. This relatively flat area called the Interior Plains, which used to be that huge inland sea. The Canadian Shield, which were our old ancient mountains. We've got the Appalachians over here, and we've got a small little mountain range up here called the Inuitians. Now, I must admit, your map, it looks a little bit different. The whole northern part, it's not very well established because not a lot of people spend time researching up there. So whatever your textbook has drawn for the north, follow it. Don't worry about the lines up in the north that your map has. All right, so hope you enjoyed the lesson today. I know it was really quick, but you can go through the slideshow at your own pace.